Greetings, folks. It's Professor Fiore back one more time. Today we are going to talk about the JFET common gate amplifier. Now, if you haven't looked at the sort of accompanying similar common base amplifier video, it's a good one to look at it at the same time. These two amplifiers share a lot in terms of performance parameters. They are both voltage amplifiers that are non-inverting. They both have relatively low input impedances and relatively high output impedances. So they're usually not the first choice for something like an audio amplifier, which might need a higher input impedance, but they work well at higher frequencies. The JFET version, the common gate, tends to have an input impedance that's not quite as low as the common base, but it doesn't produce quite as much voltage gain. All right, so our goal is to find three equations for this. Number one, how do we find the input impedance? Number two, how do I find the output impedance? Number three, how do I find the voltage gain? Right? So input, output impedances, and voltage gain. Well, before we get into that, we're going to have to do a little DC bias on this, little analysis. I'm going to need to find the drain current. I'm going to need to find the GM value. We usually need the GM, the transconductance, for our AC calculations. Now, if it's not immediately apparent, this is a self-bias. I realize it's drawn kind of weird compared to the way we usually draw it. It's sort of on its side. Normally, I would draw a JFET like down like this, right? The drain resistor would come in to the drain. I'd have my source resistor down here, ground. Input would be coming in on the gate. Well, in this case, since it's common gate, right, the gate would be going to ground, and I'd have my input coming in down here, which is a little sort of cumbersome to draw. So all I've done is I've just rotated, flipped this thing around so that the source is up here, right? Flipped it around so the gate's on the bottom. But it is self-biased because, again, we know that in self-bias, there's no external power supply attached to the source or the gate, and the VGS, the DC VGS value, is the same as the DC voltage across RS, and that's the case here. Right? When you look at this, we've got this node and we've got ground, that potential, they have to be the same. So this is self-bias. So we're going to go over to our self-bias graph and figure out, right over here, we need the ID over IDSS, and down here we need the GM0 times RS. So I am going to need some data points to start with. Now I could go to the manufacturer, in this case on Semi, and look up some things. They tell me that the IDSS is between 2 and 9 milliamps, typically 6. They tell me that the GM0, right, the maximum GM at VGS equals 0, ranges from 1.5 to 5.5 millisiemens, typically 4 millisiemens. That's a little bit of a range, and certainly the typical values will give us a starting point. It'll put us in the ballpark. You know, if I was in lab doing this and I had some transistors, I would just measure the values for IDSS and VGS off, and from that we could calculate the value for GM0, right? We have a little equation for that. It's easy enough to do. It only takes an adjustable power supply, DC power supply, and a DMM. As a matter of fact, in the lab manual that accompanies the text, there is an exercise. The beginning of the exercise, the bias, DC bias exercise, shows you how to do that. It's a fairly straightforward process. So you can always check that out. And of course, just like the text, the lab manual is a free OER. You can download that for free on my websites, or you can get a very inexpensive paper copy off of Amazon if you so choose, right? Open educational resources. All right, so what I'm going to do here is I'm going to check what Tina is using internally for the model. If you don't know how to do that, just open up and double click on the device and you get the little property page. Click on the little ellipsis next to the name and up come all of the parameters for this device. Names are a little bit different, but it's what we need. So the first one at the top is the threshold voltage. That's VGS, right? After all, VGS is the threshold, right? VGS off is the point where the VGS turns off the current, the drain current. So they're giving us, for the model, negative 2.88 volts. Another thing that we're going to need is the GM0, right? The maximum GM that we would get at VGS equals 0. They happen to call it lambda. It's roughly 3.17 millisiemens, right? All righty. So let's go back to our self-bias graph. So we're going to use those two things, right? GM0, 3.17 millisiemens, VGS off of negative 2.88 volts. So I'm going to take this equation. From that, I can get the IDSS value, okay? Now, typically, we would have this equation set up in a slightly different form, and we would find the value of, let's say, GM0 from it. But in our case, we have GM0, so we're just going to find the IDSS value. All right? Okay, so far so good. Plug the numbers in. 3.17 millisiemens, a VGS off of negative 2.88, all right? And then we're going to divide that by 2, and we wind up with 4.56 milliamps for the IDSS. Now that I've got the IDSS, right, that's half of what I need over here for the ID over IDSS. Ultimately, I want to find that ID value. I'm going to come down here onto the horizontal axis. I have the GM0, and I know the value of RS, the biasing resistor in the source. All right? That's this 2K ohm resistor. All right? 2K RS. So I take the GM0 and the RS, multiply them together. Right? That's my axis down here. So the GM0, 3.17 millisiemens. The RS is 2K. Right? The K ohms and the millisiemens cancel each other out unit-wise. That's a pure number, right? So it's just 2 times 3.17, which is 6.34. So we're going to find that on the horizontal axis. Note this is a logarithmic scale. So here's 1, 2, 3, 4, 5. There's 6. Okay. I'm just going to bring that up, hit the red line. So, we need 6.34. We can just estimate. It looks pretty much where the red line is going through this horizontal subline, right? Bring this back. And we can see that's at approximately 0.18. In other words, the ratio of IDSS, of ID to IDSS is 0.18. So ID is 18% of IDSS. Immediately, I can just multiply that by IDSS, right? So you take your 4.56 mils times 0.18, and you got your ID value, right? So I put that down here. It's just over 0.8 of a milliamp. 0.826 milliamps, or if you prefer 826 microamps. But I'm really interested in getting that GM value. So we're going to use a relation that the ratio of GM to GM0 is equal to the square root of ID over IDSS. Right? Unfortunately, I don't have a square root symbol I can use on this, so I just raised it to the 0.5 power. Yay, math. Okay, so I know ID over IDSS is 0.18, so I take the square root of that, and that works out to approximately 0.42. So GM would have to be this quantity, 0.42, times the GM0 of 3.17 millisiemens, right, what we got up there, and that works out to 1.35 millisiemens. We're going to need this again. Now, knowing that we have about 0.8 mils, we can go back in and check the DC values, the DC voltage values in the circuit. So if I have about a little over 0.8 mils, you put that through a 2K, you're going to get a little over 1.6 volts. So I would expect the source to be sitting at about, 1.6 and change, let's call it. And same sort of deal, I take that current and I pass that through a 6K, a little over 0.8 of a mil. That's going to give us about, 5 volts across RD. We have a 15 volt power supply, so that's going to leave us with about 10 volts sitting at the drain, right? These are our DC potentials. So let's just pull these up. I'll put them up here. All right, so those are the values that we would expect. And let's go in and do a little DC analysis just to do a sanity check, right? Let's just make sure things look okay, that we're not, out in space somewhere. All right, so check a couple of voltages. So node 3 is VS. We were expecting 1.65. We're getting 1.61. That looks pretty good. Pin 5 over here is the drain voltage. We were expecting 10. We're getting 10.16. So just a little bit off, right? But this is looking pretty good. Don't forget, we're reading the value off of the self-bias curve. So is it exactly 0.18? Probably not, but we're right there, right? We're within a percentage point. So that's looking pretty good. Let's check the current, right? The source and drain currents, of course, should be approximately the same. And we can see that that is, in fact, a little over the 0.8 mils. We were expecting 0.826. We're getting 0.806. All right, well, I'm pretty happy about that. That looks good. I know the DC appears to be operating correctly. So the next thing is, the important thing is, the thing we're really here for is the AC equivalent. So what do we do for AC? Well, what we always do, right? We short out these coupling caps. Boom, boom, that goes away. The DC power supply, we also short that. We replace it with its ideal internal impedance, which is a short. And we would see RD essentially going to ground. So I'm just going to mentally flip that upside down, right? Instead of having RD come up and go to ground, why not just put ground down here and we would see RD over here. Okay, so we got RD, our load, C2 is shorted, C1 is shorted, we have RS. The only other thing we need to do is throw in a model for the transistor, all right? So here is our AC model. And what we can see is RS, the biasing resistor, RD flipped down, the biasing resistor on the drain, and the 12K, our load. And here is the transistor model itself. I've done one thing here, a little different, and that is you'll notice I've labeled the current source ID as GMVSG instead of GMVGS. And the reason for that is because we're driving the source and I have a positive input over here. So I've got plus to minus on the generator, top to bottom to ground. That's applied to the source. So with that polarity, I have plus to minus source to gate rather than gate to source. And with that polarity, right, the current would be coming in, ID would be going in this direction. So that's the only reason I've done that. I flipped that because it's source to gate for this particular direction, and that direction of current is going to flow down through this load and produce this polarity, plus to minus, top to bottom, on V load. We need to keep track of that. I need to know whether or not this is an inverting or a non-inverting amplifier. So that's the only reason I've done it. If that bothers you, just think VGS, because ultimately what this really is sort of a double negative. All right. So as a matter of fact, I'm just going to be talking about VGS mostly from here on out. Okay. All right. So given this model, there's three things we can find, right? The output impedance, the input impedance, and the voltage gain. So let's go after the easy one first, right? And that would be the output impedance. Well, this would be a very similar sort of situation to a common source amplifier, or for that matter, a common base or a common emitter amplifier, where you're sitting out here on the drain, or in the case of bipolar, sitting out on the collector. Here's your load. You look back in. What do you see? You see the biasing resistor, in this case RD, and then you see this impedance, which is effectively the impedance of the current source that's driving this, the GMVGS current source. What is that? It's huge, right? It's going to be a lot bigger than the RD value. So we can just approximate the output impedance as whatever this biasing resistor is, in this case 6K. And we're done, all right? All right, next thing, voltage gain. What do you get out versus what you put in? What's V load, what's V in? Well, the V in is pretty straightforward, right? That's your VSG or VGS if you prefer, right? That's what we're throwing in here. And what we're getting out is this potential V load, which is just by Ohm's law, whatever ID is flowing through this AC resistance. So your AC load resistance, your AC RD, would be RD, the biasing resistor, in parallel with our load. In other words, 6K in parallel with 12K, right? And then we have this current ID flowing through it. All right, so if we think of that in terms of a formula, then you're talking about GMVGS, right? There's the VGS again. GMVGS times the resistance. On the input, V in is VGS. So what ends up happening is you have a VGS over a VGS, they cancel, and you end up with a gain that's just GM VGS. No inversion, right? Positive input gives me positive output. So unlike a common source amplifier, right? We have the same magnitude as if it was an unswamped common source, in other words, GM VGS, but there's no inversion. And that's an important thing to remember, right? There's no inversion out here. Okay, so now we've got an expression for the gain. We've got an expression for the output impedance. What about the input impedance? So we're sitting back here looking in. What do we see? Well, we do see this biasing resistor RS, but there's also an impedance looking into the source itself. Okay? Z in source, if you will. When we did this with a common base BJT amplifier, we'd say, what's Z into the emitter? So we're saying the same kind of thing. What is Z into the source? Right? Well, how do you find that? We always go back to Ohm's law, right? So it's a simple question of what's the voltage, what's the current? Well, the voltage is VGS. The current coming in is IS, but IS and ID are the same thing, right? They're the same size. And ID is GM-VGS, so when you divide that out, all right, the VGS values cancel, and you just end up with 1 over GM. So 1 over GM is the Z in source, if you will, and that winds up in parallel with RS. Usually 1 over GM is going to be less than RS, and is the dominating factor, okay? All right, so just to look at the numbers on here, recap. RD is the DC value of 6K in parallel with 12K, right? So 6 in parallel with 12 is 4K. That's a 2-to-1 divider, excuse me, a 2-to-1 ratio. So we get 2/3 of the smaller, 2/3 of 6K is 4K. Don't even need your calculator, all right? And then we come over to our voltage gain, right? What we got out versus what we put in. So we know that's ID times RD for the load, VGS for the input. ID is expanded to GM VGS times RD. The VGS is canceled, and we're left with GM RD, no inversion. So plug the values in, right? We just found the RD is 4K, and the GM value we found earlier, right? We found earlier at 1.35 millisiemens. So I plug that in, 1.35 millisiemens in 4K, and we get a gain of 5.4, non-inverting. Yay! Now let's go over to Z in source. Like I said, it's your voltage divided by your current. So the input voltage is VGS, the current's ID. Expand this out, VGS over VGS, that cancels, and we're left with 1 over GM. Right? So we know the GM value, right? We know that's 1.35 millisiemens. So we can just plug that in, 2K for the RS value. The 1 over GM works out to 741 ohms. So we put those two things in parallel, and we get 541 ohms for our ZN. Not a very big value. This is what we expect. Again, I'm going to draw a parallel, no pun intended, a parallel over to the common base amplifier. We don't see a particularly large input resistance for a common base amplifier. You know, the Z in emitter is pretty small. It's a function largely of whatever our prime E is. So, you know, 1 over GM is kind of like R prime E for a bipolar, right? They are similar in terms of they describe what's going on with an input parameter versus the output current, okay, the ID in this case. So that's what we see, a mere 541 ohms. We have a 60 ohm generator, so we're going to lose a little signal there, but not a tremendous amount, all right? Okay, so let's go back to our original circuit. So let me bring up those calculated values that we expect. All right, so gain of 5.4, a ZN of 541. Now, what I want to do is some AC sims just to see if, in fact, this is correct. So the first thing I'm going to do is take a look at the voltage gain. We'll just do a little transient response on this. Now, there is going to be a small amount of loss on the front end. We have the Rgen of 60 ohms, and this, looking in, is 541. So there is a divider. The voltage divider out here, you got 541 over 541 plus 60. In other words, 541 over roughly 600. You're going to lose about, coarsely speaking, without getting out my calculator, about 10% of the signal. So if I have 10 millivolts coming in, I expect, given these numbers, to get about 9 millivolts. Like I said, I'm going to lose about 10% because of Rgen. About 9 millivolts out here. Okay, and then that is going to be multiplied by our gain, and we'll see the appropriate load signal out here. I've kept this pretty small because I don't want to see a lot of distortion in this amplifier. Again, there's no swamping characteristic here. JFETs tend to have lower distortion than bipolars, but they don't have as much gain. So it's maybe not as bad a situation as it is in a let's say, a common base, but we still don't want to put in really, really huge input signals. We'll get a lot of asymmetry in the waveform. We're also going to check this 541 in just a moment, but let's go up and do this transient analysis. So I'm going to go from 1 to 3 milliseconds, or skip over the turn-on transient. So we'll get 2 cycles out of here since I'm running at 1 kilohertz. And let's bring this over here so we can see it. Ba-ding, ba-ding, ba-ding. All right, now I've got some colors here that are kind of similar. So I'm going to change the color of that one. Oh, let's use something, how about blue? That'll work. Oh, that's much better. All right, put our legend out here so we can see what's what. So that blue is the generator. That should be the 10 millivolts. The maroon is Vin. We can see that's just a little bit down. And then V load is this much bigger signal. So first I want to zoom in and verify that we're getting about what we should be getting. All right, so let's grab a cursor. All right, so there's our 10 millivolt peak. It's 9.999, whatever. And now let's go over and look at V in. Okay, input to the amplifier proper. And we should be losing, like I said, around 10%, so 9-ish millivolts. So here we're getting 9.03, and on the negative peak, we're getting 9.02. All right, so that looks good. That makes sense. I don't have any problems with that. That's pretty much what we expected. And now let's take a look at our output. And we are getting about a little over 45 on the positive peak. So remember, our expected gain is 5.4. We've got roughly 9 millivolts coming in. So 9 times the 5.4 is going to get us, 46, 47. We are a little shy of that, 45.2. Come down here, we're getting 45.8. So that's indicating there is a little bit of distortion in this amplifier, that asymmetry that we see. And we can check on that in just a second, right? But that's certainly in the ballpark, okay? That's about what we would expect to see. Notice everything is in phase, right? A non-inverting sort of amplifier. So we're getting voltage gain, but no inversion. Cool. All right. Let's go check the distortion on here. So we'll come in and we'll grab the Fourier analysis. And on the output end, I want to look at V load. And we're getting about 0.16%, okay? Which is, as I would say, it's not exactly super hi-fi, but it's not really grungy either, okay? All right, now I also mentioned the input impedance. How do we double check the input impedance? Well, the obvious trick that we've done before is, hey, it's really just a voltage divider. So why don't we set our gen to the expected Zin? If we do that, or if I take the Rgen and I set this to 541 ohms, and we're exactly correct, okay, then what should happen is I have a 1-to-1 voltage divider. So this 10 volts should split evenly. I should see half of it, 5 millivolts here, and the other half, 5 millivolts out here, right? Because this whole thing looking in, right, looking in here, supposedly is equal to 541 ohms. So if they're identical, this voltage should split in half, right? It's a very simple way in a lab to check what your input impedance is, because after all, you cannot use an ohm meter on something like that. All right. Okay, so let's go into the transient. Do this again, see what we get. Okie dokie. Just to be consistent, I'm going to change the color on that one so there's no question. We made that blue. All right. So that blue is supposed to be our 10 millivolts. And let's just, for the sake of completeness over here, let's just check that. Right? Yeah. 997. So 10. Now I'm going to grab, this is the VN. As a matter of fact, let me put the legend down here just so that there's no question. All right, so the VN over here is the maroon, and I am going to move this around, and looky, I'm getting a smidge over 5, right? 5.1 something. Let's see on the negative end, same deal, roughly 5.1 on both cases. So we know that we're getting roughly half the signal, so it's not exactly 541 for our Zn, but it's pretty darn close. All right. All righty, so there we go. The device that we have, little JFET, is producing a voltage gain, a fairly modest voltage gain. It is non-inverting. We're getting a modest sort of input impedance, not really, really high, but not crazy low either. And there you go, one more sort of item in your kit bag, a common gate JFET amplifier. Hope you enjoyed it.